take a look at what we have today. We have, I need to give the permissions to share. And so last time we mentioned that we want to discuss on the composite quadrature rule, and then this time I would just finish all the things on the composite quadrature rule, and I'm not going back to what we have we mentioned last time. I hope you have already taken a look at the lecture notes, and then go to take a look at the you have already taken a look at the intermediate value of theorem, and then you have already be familiar with this extreme value theorem. So based these assumptions, I'm going to go back to the proof. So I assume that all of you know extreme value theorem. All of you know the intermediate value theorem. So this is your after class work, and then I assume that you have finished all the after class work. And this time, let's go back to the composite rules we have. The composite trapezoidal rule I mentioned here is just like applying the trapezoidal rule to this subinterval, this small interval here, and I do the calculation here, and I leave this this raw error terms here without any processing. And this is just the composite quadrature rule, composite trapezoidal rule. And last time we just stopped here. We have this raw error term, and then we want to process it and get a common c. We want to get a common c here. And we also mentioned that this is the error term. We want to, there's some delay here. I'm not sure what's happening today, but there are lots of delay between the Zoom computer and then Zoom iPad. Hey, wake up, computer. It's already 11, you should wake up. Yes, you can see, I'm not writing. Okay, it's not working, and the iPad or the computer is still in the weekend mode. Let me see. Should I connect to other network? Maybe use this one. Please. Okay, good. Okay. Okay. I think the connection is better. So let's get back to what we have here. We have the every time, and then last time I do some processing here, and I just take the H. This is the 3H here, and then I just take 2H out, and then 1H I put it here, and then I replace the H with this expressions here, because the H is just the step size of the subinterval, the size of the subinterval, and then the size of the subinterval is just the b minus a divided by n. And so here we have b minus a, and then I put the 1 over n here. And this one, and then is something similar to
if you go back to the high school and then you immediately know, and then we have n times n and divide by n, and that's the average value of these n items. And now we are going to get a common c. Can we do this? Can we do a equal sign and then find a common c here, and then it equals to second derivative divided at 1 c, 1 common c. Yes, let's do the processing here. And first of all, we are going to use the extreme value theorem to get the maximum and minimum. The extreme value theorem implies that the second derivative, because we assume that the second derivative here is continuous, and because we assume that the f function is belonging to the second continuous function space, and which means that the second derivative is also a continuous function, and because it is continuous, and then the extreme value theorem implies that this function, it can achieve the maximum and minimums on the interval a and b. And so we have the bounds, the lower bound here, and then the upper bound for the second derivative evaluate at the Cj. Cj is a point in the interval a and b. So now let's do the calculations. Let's do the sum and then take a look what we have. And I'm going to sum up all the second derivative evaluated at the Cj. We have n Cj here, different Cj here. They are different. Cj1 could be different from Cc1, Cc2, and then we also have Cc0, and then Cn minus 1 could be different. They could be different. So we need to get one. We want to get one common Cc to get a nice format. And so now let's see. I'm going to sum up all the Cj here. Let us sum up the equality so let's say this is the equation 1 or equalities 1. Let us sum up the equality 1 for j equal to 0, 1, and then to the n minus 1, and we get this. Summing up, and then j equals to 0, and then n minus 1, and then f second Cj. And so for the right hand side, we still have the maximums, and then the maximums does not change because that is the only maximums we have. It is unique. The second derivative maximums on the interval is unique, but we have if we sum them up, and then we have n maximums here. And on the left hand side, we also have the n minimum on the left hand side. Any questions so far? So this is just like we have the so for example here we have the let me just do the copy and paste very fast, very quick. And this is just a summation. Let's see. So first we have the Cz0, and then we have the Cz1, and you will see I just changing the index here, and nothing is changing here, and then nothing is changing here, and then I add all this inequality stuff, and then I get this is sigma sum, and then I get n piece of the maximum, and then I get n pieces of the minimum here. So that's what I'm doing here. And on the left hand side and then on the right hand side, you will see the n
this is the n, the number of the CJs we have, and let's do the calculation, dividing the inequalities by n, and we get this. We get on the left hand side, the most left turn, and then we have the n items and minimums, and then divided by n, and then we get the minimum. And this one, and then divided by n, the middle term here, and the rightmost part, and then we got this. We divide the right terms here, and then by n, and then we get the maximum. Okay, that's something similar to what you have in the intermediate value theorem. And let's go back to take a look at the intermediate value theorems. The intermediate value theorems is stating that between the maximum and the minimum, and if you pick this is the maximum and this is the minimum, and if you pick any values between the maximums and the minimum of the value, the function value, let's say this is k, and there is a point in between this domain, the x domain, and then we can find a point, and then that's corresponding to that value you pick. So this value is between minimum and maximum, and that's some things you have. You just have. You have a value in between the maximum and minimum of that function. And let's see. So this function here, that's your k. This number is your k. And this is your function. Do you see this? This is the intermediate value theorem. So you have the maximum of the second derivative function, you have the minimum of the second derivative function, and you have your k value for this. This is the k value. It's just the average of this number, right? And then you can treat it as a constant. And so this is the value between the maximum and the minimum. And this is your k. And by the intermediate value theorems, you have this. So there is a point between the A and B, and then it equals to that intermediate value value k. So let's see by the intermediate value theorems, we have, because you can check this part as your k in the this is your k in the intermediate value theorems, and we have there is C and the interval A and B, such that we have that this is the function, and then this the function is second derivative of the f function. So we have the second derivative function. This is the functions in the intermediate value theorems, and then it evaluates at C, and then this function's value it equals to the k value we pick. And on the right hand side, that is just the k value. And this is our k value, sigma sum. Sigma sum j equals to 0, and then second derivative cj. Any questions here? The applications of the intermediate value theorems. We have the maximum, we have the minimum, and then we choose k value in between, and then that k value it's just the average of the second derivative evaluated at the Cauchy. And by the intermediate value theorems, and then we have the Cauchy in between, and then this Cauchy evaluate at this function, and then this is the same as the function we have here, and then it's just equals to the K value we pick. And then the K value is just the average. Any questions here? You might need to use this sometimes in your homework. I'm not sure if we have a homework in this weekend about this. I think I can compose one. The last quarter they don't have such a questions, but I can create one. It's good to know about this. This is a common technique to use. And next, so we have already finished all the things. So we get the common Cauchy. Let's get back to the conclusion. So here we have at the end, this is the error term, and then we can rewrite the error term, this one. Please do some copy and paste for me. And this one, so at the end, the error term, it should look like this. This is the error term of the composite quadrature rule, trapezoidal rule. And now let's see. So I just write the average of this one as a common Cauchy. So at the end, we get this. It's the negative 1/12, and then b minus a, h squared here, b minus a, and I got the common Cauchy here, second derivative Cauchy. Where the Cauchy equals to, it's belonging to the A and B. And I'm going to erase all the things in between and then just keep the conclusion here. And this is the conclusion. And okay, this is the conclusion. And I believe there's one conclusion somewhere. It's here. The conclusions we have the this part is the first part. The first part is the trapezoidal composite trapezoidal rules, and then this part is the error part. And if you have a question about how to if you have a questions about applying the composite trapezoidal rule to calculate, to get the approximations of the approximation of the integral, then you need to first, if it is saying, if the question is saying the n equals to 10, right? N equals to 10, and then the interval is, let's say the interval is AB equals to 0 and 1, and then let's say the f function it equals to the exponential function. And what you need to do is to first get the node points, and then this is 0, and then 1, and then because n equals to 10, and then you have the h size equals to 1 minus 0 divided by 10, and then that is 0.1. And you need to get your node points, and then your node points, and then it's just the x0 equals to 0, x1 equals to 0.1, x2 equals to 0.1, 2, and so on and so forth. We have the xn minus 1, and then it equals to the it equals to x9. This one it should be x0, x1, 1 interval, and then 9 interval, and then it should be 0.9. And the x10 is just the endpoint. The right endpoint is x1. This is equals to 1. If you want to calculate the approximations of the integral, and then you need to use this formula here to get the approximation. And for example, here h equals to 0.1, and then you need to calculate this, and then 0.1 divided by 2, and you have FA is just with the coefficients 1. So we have this one is with the coefficient 1, and we can do exponential. This is the function we define here. Exponentials 0 here because it's just a value, the a point, the point A. And all the things in between, it should be with the 2 coefficient, and we evaluate the function at the x1, x2, and then to the n minus 1, and xn minus 1, and then xn minus 1 is just the e exponentials, and then 0.9 here. And we also have the right endpoint, and then it should be exponentials 1. And you need to use your calculator to calculate this value, and that's the your final answer. Does that make sense? And let's compare what we have for the composite trapezoidal rule and the simple one, okay? So let's say we are going to use the simple trapezoidal rule to calculate this. And what is the difference between this one and the simple one? And let's see. That's interesting. So FAB FX dx, and then we have the H2 and FA plus FB, and the error looks like this. And very first, you will see, actually we can change this to some H size, right? Because B minus A divided by N is just the H size. But we use the constant here. Here, this is a constant, and this is the constant 1/12. And if you compare this, and then you will see, maybe this one is more accurate because you have the H to the other 3, but you need to be very careful because we are saying this is the state interval A and B, right? If you are using the composite trapezoidal rule, and your H size could be very small. It's like H divided by 10 here, right? But here it's just the H size. So this number could be smaller than this number because this size here is not the same as the H here. It is the H divided by N compared to this formula. Does it make sense? So usually we would get a more accurate results from the composite trapezoidal rule. And in the in practice, we usually use the composite one, and then the simple one, seldom people use it because the approximations of cells is not accurate enough. Any questions? No, this is too simple. So let us get some more difficult things. And we are going to do the same process for the Simpson's rule, and we are going to divide the intervals into n parts, and then we apply all the things to the subinterval, and then we would get the composite trapezoidal rule, and we would get the error stance as the process we have done before. So let's see. I'm going to divide this interval A and B into the n intervals, and then I'm going to apply the Simpson's rule here. And if you take a look at the blue line, this is the actual f function, and then the this line here is approximated by the Lagrange polynomial, or the Taylor equation, the Lagrange polynomials with 3 points, the middle point and the 2 points here. And so now we just apply the Simpson's rule for each subinterval, and we will do the same process. I'm going to repeat the whole process here. It's nothing new compared to the trapezoidal rule, the composite one, but we are applying different things to this interval. And wait a moment. Here the trapezoidal rule is not applying to this x0, x1. We are applying the Simpson rule, not the trapezoidal rule. We are not applying the Simpson's rule to this subinterval. We are applying the Simpson rule to this subinterval, x0, x2. This is the middle point. This is the middle point, x1. So let's see. I should have some assumptions here, and then we assume that we have the n interval here, and then this n should be the even number. And we assume this, and then we go to take a look at how we apply the Simpson's rule to this n interval. And we have the x0 and the x2. This is the subinterval we have, and then fx dx, and then plus the x2 and then x4, and we just divide the integrations into n divided by 2 parts. And the last one should be n minus 2 to the n and the fx the x. And I'm going to rewrite these things into the sigma sum, and then the sigma sum, it looks like this. The sigma sum here is just the j equals to 0, and then this is the let me see, this is j equals 0, and then to the j equals to should I write this? Maybe I'm not going to use the sigma sum. It will make the notations complicated. So let's just apply the Simpson's rule to each subinterval here. And for the first one, and let's recall what we have in the Simpson's rule, and also what we have in the here for the step size. The step size is the h equals to the b minus a, and then divided by n. And then from the Simpson's rule, let's see, this is the Simpson's rule. We have the 1 here for the left endpoint, the middle point is 4, and then the right endpoint is 1. And then we have h divided by 3. So what we have here is, let's go back to here to apply the Simpson's rule to the first interval, and then we have the h divided by 3, and the first one should be fx0, and then plus the 4fx1, and then plus the fx2, right? So by generally we have this. So we have applying the Simpson's rule to the intervals xj and then xj plus 2, and then we have we have this below. We have xj integrate from the xj to xj plus 2 and the fx dx, and then we have h divided by 3, and then the left endpoint is just fxj, and then the middle point is the xj plus 1, but it's with the coefficient 4, and the right endpoint is with the coefficients 1 again. And this is the general things for each subinterval. And if we apply this to all of the subinterval here, and then we get at the end, we are doing the summation here. So for samples for the subinterval here, this is the first one, right? And then this is the first one, and then we need to do some very careful calculations here. This is the second one, and let's see what do we have. We have fx2 again. This is the left endpoint. Once again, we have the fx3, but it's with the fourth coefficient, and we have the fx4. And let's see one more turn here, okay? And we have the fx4, x6, and then let's take a look one more turn to see the patterns here. We have the fx dx, and the things in between, it should be the 3 dots. And let's say we have the third turn, and then we want to apply the sim substitute to this third turn here, and then what is the result here in the approximations formula? We have it equals to, so for the integrations between the x4, x6, and then we have this. We have once again the coefficients of the left endpoint is x4 is the coefficient should be 1. And then the middle point is the x5 of that interval, and then it should be with the coefficients 4. And then the right endpoint here, it should be with the coefficients 1. And do you find any pattern here? For the odd number, what is the coefficients? You are going to add all the things up. 4, right? Because if you take a look at here, 4 here, nothing is repeated, but 4 here, and then 4 here. And then except for the endpoints, and then what is the coefficients for the even index term? 2, because this one is repeated. And then this one is repeated, right? And so now, what's the coefficients for the endpoints of the entire interval? Just 1, right? Because at x0. And then at the end, you have, let me just write that down in case the things is so confusing. So at the end, we have, so for this item, for the last item here, and then we got this. F xn minus 2 plus 4xn minus 1, and then plus the fxn, and then you will see immediately from here, the last item is with the coefficient 1. So let me conclude this. At the end, if you do the summations here, you would get such a formula, h divided by 3, and then fa, and plus, and then 2 is for the even index term, and then this j is different from what we have just now. I'm going to doing some re-index here, and then this is for the 2j here, the subscript here, 2j. It's 2j. It means that this is the U1 index term. And the U1 index, it should be from the 2 to the n minus 2. So here, n minus 2. So if you change the j to this number, and then it should be the 2 times this number here in the subscript. So that is corresponding to the n minus 2 here, the index term. And we also have the 4 coefficient for the odd-Lumberton. Let me just put it here. This is the E1 index item. And we are going to write down the, this one is the odd index item. And the odd indexed items, I can write it with j equals to 1, and then it's summing up from the j equals to 1 and to the n minus divided by 2, and the odd indexing could be expressed as 2j minus 1. And if you take a look at here, if I substitute the j equals to 1 here, it's just the 2 times 1 minus 1, and then this equals to 1, and it's corresponding to the first odd index term. And if I substitute the j with n divided by 2, and it's corresponding to x, and then n minus 1. Does that make sense? So if I substitute the j equals to n minus 2 here, and then the x 2j minus 1, and then it is just the x n minus 1. Let me see. Yes, it is. Does that make sense here? So the x n minus 1, once again, is this item here, and then it is the odd index term here. And then for the first one, if you substitute j equals to 1, and then it's just 2 times 1 minus 1, and then this is just the first item, first odd index item. And that's all the things about the Simpson's rule formula. And the next, we cannot finish all the discussions here, unfortunately. We also have the last things. Sorry, there's one last things. It's the right endpoints with coefficients 1. But next time, I'm going to talk about the error terms again, about the Simpson's rule, and then we will use the same technique here to get the common cosec or common eta j. So one thing I get missing here is, so this is not the equal side. This is not true because the right-hand side is the approximations, right? And then the left-hand side, this is just the approximation, and then this is the exact value. And actually, we should have something here, and that represent the error term. And let's write down this. And next time we will analyze the error term as well. So for the error terms for this subinterval, we have minus 1 over 90, and then 4 digit eta j, and then h to the other 5. And where the cosec j, where eta j is in between the xj and xj plus 2. This is something we have learned from the last class. And this is at the very beginning, there's a conclusion here. It's 1 over 90, and then h to the other 5, and then 4 digit. And then cosec is between these 2 points. And we just apply this to that subinterval, this very little subinterval here, the xj to the xj plus 2. And then we have the, we apply that Simpson's rule to this subinterval, so that we have the error term looks like this. It's the productive evaluated at the eta j, and then we have h to the other 5. Does that make sense? And now, if you do the summation, and then you will see immediately that right-hand side here, this is just the approximations formula, and then we should have an error term here. And that error term is just summations for that error terms, and then we are going to sum up all the error here, and then we have the summations. It looks like this. We have the summation 1 over 90, and then f4 eta j, and then h to the other 5. And how many do we have? we have sigma sum j equals to, let me see, it should be, we have 1 and then n divided by 2, right? Because it should be yes, j, yes, we have n divided by 2 interval. So we have n divided by 2 errors. And we are going to deal with this next time. And we would get a common C for this error term. And one comment eta, and then in between the A and B. And this is the next class material, and that's all the things we want to mention today. And then class is dismissed. And if you have any question, and then you can come here to get the answer. Here is a code at the end, and there's a code at the end of the lecture notes, and then you can go back to your home and then try out that code and to play around with that code to see how to apply the composite stem-sum rule and composite trapezoidal rule to the actual cases.
I just realized at the start of class, I forgot to upload my code for homework too. So can I like send you an email with it? Or
You can send an email to the TA.
Okay.
I'm not grading the homework.
Okay, yeah. Thank you.
For the code, actually you can resubmit the PDF of the of your solution, and then for the code you need to submit not the IPNY, not the Python code file. You're going to submit the PDF file. That is the screen capture or the or export the code to the PDF file.
Okay.
Homework 3, the one we have, we are deriving the error term for Simpson's rule, and we you have the code on campus. Do we need to rewrite that code and post the code, or can we just get our 4 equations, however many unknowns, whatever, be we have this, we used Python code that we have.
Yeah, you can do that. Yeah, the latter one. Yeah,
Okay.
you don't need to change anything, but you need to write down that process. So you need to. So the Python code is just for calculations, right?
Yeah.
But you need to write down how you get these formulas on your written solutions.
Yeah, I have n equals 0 to n equals 3, and then I use n equals 4 later. Okay, but I don't
But
I don't need to actually submit the code.
Yeah,
Okay.
the Python code is just the calculators.
Yeah, so I don't sit there. And
Yeah,
good.
good.
Thank you.
Good understanding.
So for the homework 2, were we supposed to submit a code for the?
The code is the code file. You don't need to submit the original code file, but you need to export the code files to the PDF file. And you have the PDF file for the code, right? And then you have the PDF file for your handwritten solution, and then you can use some online to combine to one PDF file.
Okay, so I was gonna do that for the last homework, and then I just completely blanked my mind. So is there anything I can do to submit it now, or
You can definitely resubmit it.
just
there.
add it? Okay. Okay.
Yeah,
Cool.
just
Thank
add
you.
it.
Thank you.
You can just, there's a button to replace that PDF.
It's resubmit, right?
Yeah,
And I can
resubmit, yeah.
Combine my written with the code into one
If-
zip file.
If the Grayscale don't let you to do so, and then you can send an email to the TA to override that permissions.
Sweet. Okay, thank you.
Questions? No question, and then I will go to have my lunch.
Thank you.
Bye bye. 再见，再见，说的，多多。